Hello. Okay, so let's start with the talk. Today I will cover some of my research on Apache HTTP server, and I will show you also some of the vulnerabilities that I have found during this process. But first of all, who am I? Well, I am Antonio Morales. I work as a security researcher at GitHub. That is my Twitter handle, where I usually post most of my research. And inside GitHub, I'm part of a small team called GitHub Security Lab. Our main goal in GitHub Security Lab is to improve the security of the open source software. This is just an example of our work, and I encourage you to go to our web if you want to know more about our team and the research that we do. In my case, I am mainly focused on C and C++ projects. I'm also a Fuzzing enthusiast. I'm more specifically a fan of AFL. And these are some examples of software in which I have been working on during the last year. But today I'm going to focus only in the Apache HTTP server. Okay, so the agenda for today has these 5 points. In the first one, I will show you a brief introduction about the Apache architecture. In the second one, I will show a summary of my fuzzing workflow. Then I will go over some of the custom mutators that I have built and why I have built these custom mutators. After that, I'm going to explain some of the custom interceptors that I have created. And in the last point, I will show you some of the vulnerabilities and bugs I have discovered. Well, let's start with the Apache architecture overview. Apache is one of the most well-known web servers out there, so it doesn't need any introduction. So I can skip this slide. And okay, Apache architecture is composed of 3 main parts. The first part is the core. It includes some basic functionalities of Apache. Then we can find the modules. The modules implement most of the functionalities of the web server. And then we have the APR library, the Apache Portable Runtime Library. Between the modules, we have 5 different categories. The first one is the npm module. This type of modules are responsible for basic request handling and dispatching. Then we find the base modules. These modules are compiled and loaded by default. Then we have also the extensions modules that are not normally loaded into the server, except for a few cases. We can find also the experimental modules. Those are available into the Apache kit, but are not officially supported by the Apache team. And the last group is the external modules that are not included in the Apache distribution. And a very important type of modules are the npm modules, or the multiprocessing modules. These provide an interface between the Apache server and the operating system syscalls. Between the tasks that the npm handle, we can find, for example, creating the network connections, listening for requests and accepting requests from the client. And npm can also handle the creation of processes and threads. And it's important to note that only one npm can be loaded at the time. Then we can differentiate 3 main modules on Unix systems. The first one will be the prefork configuration that implements just a prefork server without threads. That is how all versions of Apache used to work. The second npm configuration is the worker npm. This npm implements a hybrid, multi-threaded, and multi-process server. In this npm, each process creates a fixed number of threads. And the last one, the newest one, is the event npm. In that case, it's an asynchronous implementation. And the main difference with the worker npm is that the event npm is able to reuse a single thread for new connections. And then the last one, we have the third main component of the Apache architecture, that is the Apache Portable Runtime. APR is a supported library for Apache and provide a set of APIs that make possible to use the same functions across the different platforms. Some of the capabilities of APR includes the memory pools and memory allocations. APR also handles the file input and output, provides also shared memory functionalities, and other things as multi-threading and time routines. And this is the Apache operation diagram. It has three different phases. The first one is the Apache startup. This first stage includes the parsing of the configuration files, the loading of libraries, and the initialization of system resources. The second one is the operation phase. In this phase, the first thing that Apache does is to call the set UID in order to change to a regular user. And it also includes the request processing itself. And the third one is the cleanup phase. In this last stage, Apache releases all the resources, including memory, file handles, or the sockets. Now, I will show you an HTTP request and how this HTTP request is processed by Apache. For example, we have our HTTP request here. Okay. And at first, this HTTP request will go through the metadata modules. Then the output of the metadata modules will be processed by the input filters. After this, the request is processed by the handler modules and by the output filters. And the last stage is the execution of the login modules. Amongst the metadata modules, we can find, for example, modules for URL pre-parsing or modules for HTTP access and authentication. And as a filter examples, we can find modules for encryption or modules for compression. Well, now I'm going to explain some of the most relevant aspects of my fuzzing workflow. I have divided my fuzzing workflow in 4 different parts. The first one is choosing a fuzzing engine. The second one is socket fuzzing. The third part is important code changes. And the last one is fuzzing modules. When it comes to the fuzzing engine, I don't have any doubt. AFL is my choice. And to be more concrete, AFL++, that is a fork of AFL, but includes a lot of new features in comparison with the original AFL. Amongst these features, I can mention the custom mutators, the power schedules, or multiple instrumentation modes. Another problem that we face when we want to fuzz an interactive server is that AFL doesn't support native socket fuzzing. So we need to modify the source code in order to be able to fuzz the server. For that, my approach was to add a small code snippet to the npm code that self-connect to the server itself and then redirect the input data through it. Let's look at these two code snippets. You can see the self-connect function that establishes a connection to server itself. And what I do then is to just read the fail data and send this data through this socket. You can see it here. These two code snippets will be then introduced at the npm code. And in my case, I use two different fuzzing configurations. Most of the time, I use the prefork npm with only one process at a time, with the aim of getting a good stability. But I also fuzz the event npm in order to catch concurrency bugs. Let's see now some changes made to the source code in order to improve the fuzzing process. The first group of changes are aimed at reducing the entropy. For example, in this case, replacing calls to random by constant values. Here you can see as I comment out the APR generate random bytes call, and instead I used a constant seed. The second group of changes are changes aimed to reduce delays. For example, removing some sleep or the main idea is to improve the fuzzing speed. Here you have a more clear example. The third group of changes are those made in crypto routines. For example, to disable the checksums. In this picture, you can see as I comment out both CRC comparisons. This is the first one, and this is the second one. That's really important because the fuzzer will get stuck in these CRC comparisons if we don't disable them. And now I will show my approach for fuzzing Apache modules. What I did was to use an incremental approach where I started with a small set of modules enabled. Then I tried to progressively include new modules in the configuration file and tested the stability again. Following, I repeat this process until all the modules are enabled, and then I suppose that the fuzzing process is stable. Let's give now a brief introduction about custom mutators. But first of all, what's the problem we want to solve? Well, by default, AFL and LibFuzzer implements basic mutators like, for example, bit flipping, byte increments, or noun integers. So these mutators provide good results when applied to binary formats, but are not so good when applied to complex formats like, for example, HTTP protocol. So my solution was to include additional custom mutators, specifically created for fuzzing the HTTP protocol. You can find the code of all these custom mutators in my GitHub repository. That's the link. Okay, now it's time for examples. In this first example, we can see a simple custom mutator, the line swapping. You can see here two different HTTP requests. A GET request on the left and a POST request on the right. And below you can see an example of mutation where the content type and the accept language headers have been swapped. So now the POST request has two different accept languages headers. This is the first one. This is the second one, while the GET request don't have any accept language header. In this second example, we can see a word swapping custom mutator that just swaps two words of two different HTTP requests. And the picture below, you can see as the HTTP request have swapped their URL. You can see here the original HTTP request and just here the modified HTTP request. I have also implemented some other custom mutators. For example, I implement a Charles brute force mutator. These mutators were inspired by Hashcat password cracking tool. And for example, I implement 2 and 3 bytes brute force, string brute force, etc. In addition to use custom mutators, I use custom grammars. For this task, I use the grammar mutator tool that it is included in AFL++. To use grammar mutator, we need to define a JSON file that includes a collection of key and value pairs. Okay, so let's go with an example. This is a snippet of my grammar specification. You can see as every request is composed of an start line. Then we have an end line, or end of line, sorry, end of line. Then we have the headers, the body, and the end of the request. And every single start line is composed of a method, for example, get, head, post, the URI, and the HTTP version. This is just an example, but as you can imagine, every type of grammar specification can be defined. Well, now it's time for custom interceptors. But first of all, again, why do we need to implement custom interceptors? So, as I previously mentioned, Apache uses custom memory pools to improve dynamic memory management. For this task, Apache uses the functions that APR provides. For example, if we want to allocate memory inside the memory pool, we need to use the APR palloc instead of the standard malloc. So consider the following code snippet, where the program calls to APR palloc. In this case, the second argument is, we want to allocate 126 bytes inside the pool defined in the first argument. So the first argument is the pool where we want to allocate the memory, and the second argument set the number of bytes that we want to allocate inside the pool. And how do these Apache memory pools work? Well, the Apache memory pool consists of a linked list of memory nodes. You can see here an example. And each node has a fixed size memory available. This is the memory available. This is the fixed memory available in the second node, and this is the memory available in the third node. As you can see in the third node, there is still some free space available. Then, when more space is needed, the program will add a new node at the end of the list. And this is the code of the allocator alloc function. And the thing is that this function round up the minimum size to 8,192 bytes. And of course, this will be a problem for address sanitizers. So, for example, I can show a scenario where we made a call to APR palloc with a size argument of 126 bytes, but address sanitizer has poisoned a memory area of 8,192 bytes. You can see the original call, and you can see how many bytes address sanitizer has poisoned. So the result is a total area of 8,066 bytes marked as writable by address sanitizer, but this is not real allocated memory. Instead, it's free space in the node. So for example, imagine that we call to main copy with a size of 5,000. This will lead to an overwrite of the rest of the node's memory. But however, address sanitizer will not throw any alert message. This type of errors can result in vulnerabilities such the one I published 1 year ago in Pro FTPD. This is the CVE of the vulnerability that I released. And to solve this, what can we do? Well, we can define our own custom address sanitizer interceptors. In order to define our own address sanitizer, we need to do two different things. The first thing is to define an interceptor function where the foo is the name of the function that we want to intercept. The second thing is to call to the ASAN intercept function just before the first call of the function foo. Well, this is my implementation of my interceptor for the APR palloc function. There are three relevant parts. The first one is when I call to the real APR palloc to get the original address of the APR palloc. Then I save the address of the address sanitizer malloc. You can see it here. And then what I do is to save both addresses to free them later. Obviously, if we define custom interceptors for palloc, we will need to define also custom interceptors for free. So in that case, what I do in the first step is to free all the addresses previously allocated with the address sanitizer version of malloc. And then we can proceed to free the memory allocated with the libc version of malloc. Cool. So now it's time for the most expected part. Now I will show you some of the vulnerabilities and bugs that I have found. I'm going to start with a null dereference in the session identity decode function. As you can see here, this bug can be triggered setting a cookie with a null key and value. So look at this example to clarify the things. In the first position of the cookie, we have the session key and the choco value. In the second position we have the admin user key and the number 2 as the value. But in the third position, we have an empty key and value pair. You can see it here. We only have the equal symbol, the assignment symbol. What's the problem here? Well, if you look just below, you can see two calls to APR string token to extract the first and the second value, key and value. So that said, let's see what happened in the string token function when the first argument is null. You can see in this line how the while loop tries to dereference the first argument. You can see it here, where the first argument is the string argument. So if this argument is null, we will trigger a null dereference bug. In order to exploit this bug, mod session needs to be enabled, and this vulnerability can lead to a denial of service at the child level, affecting to the other threads in the same process. Okay, now another vulnerability. In that case, it's an stack base off by one in the check nonce function. In order to exploit this bug, the mod auth digest module should be enabled, and the application has to be using the digest authentication. For triggering this bug, we need to assign a specific set of values to the nonce field. Here you have an example. And as you can see, the nonce field is a base 64 value. So then the check nonce functions performs a call to the base 64 decode binary function in order to decode this value. The thing is, the first argument is a local array of size 8. But here below, you can see as the calculation of the n bytes decode variable is grown, giving 9 as a result. So in this case, 9 bytes will be written into an 8-byte buffer, writing 1 byte out of the boundaries of the array in the stack. Okay, let's see the third vulnerability. Here we have an useAfterFree in the cleanup_tables function. This function calls to the rmm_destroy function, as you can see in this line. And the thing is that this memory has been previously freed by the APR allocator destroy. So we are trying to access to an address that is no longer valid, leading to an useAfterFree bug. It's important to mention that this vulnerability can only be triggered in the one process mode. Another one. In this case, we have an out of bounds write in the heap, affecting to the escape quotes function. This function escapes any quotes in the given string. The origin of this bug is a calculation mismatch between the length of the input and the size of the allocated outstring buffer. In this first code, in this first code snippet, I show the code used to calculate the length of the input string, and in this second picture, you can see that the code for calculating the size of the output string is different. This is the first one, and this is the second one. As a result, if we provide a malicious input to the escape quote function, it's possible to write out of the outshared array. Unfortunately, this bug was previously reported by Google OSS Fuzz just a few days before I found it. Now I'm going to explain something totally different. In this case, this bug is a race condition leading to an useAfterFree, affecting the Apache core. So during my fuzzing research, I found multiple bugs that I wasn't able to reproduce again. After go deeper in that, I discovered a kind of race condition between allocation and destroy function of APR. This leads to a corruption of some nodes of the memory pool, and sometimes the program tries to release a block that is already present in the free pool. At this moment, I'm still trying to figure out how to exploit this vulnerability in a deterministic way. These are some stack trace examples. In this case, we have a useAfterFree. And here, a totally different stack trace related to the same problem. And the thing is that this is not a new problem. This is a problem that has been reported a few times in the last years. For example, I would like to mention to Hanobok. Hanobok reported this bug at first time 3 years ago. If you are interested, you can check it in the following link. This is his GitHub repository. And for now, the position of Apache security team is to not consider these security issues unless we can show a practical exploit. During my fuzzing session, I found a lot of other minor bugs. So I would like to show you one of them, an integer overflow in the session identity decode function. In that case, this bug is not a dangerous bug, but I think that it's interesting to show an example of how trivial it is to trigger this bug. For example, you only need to send a log web-app request with a long timeout value. So look at this line. I'm sure that most of you are able to identify what is the problem. Were you able to find the bug? Okay, I'm going to explain it. Here we have the addition of two integer values, the now integer and the expires integer. That will be stored in another integer variable. So if these values are big enough, we can overflow the return value. Since this bug is triggered with a log request, moddap should be enabled. Okay, and now I would like to say one last thought. Apache HTTP security has been extensively studied by researchers. But at the same time, there is still room for discovering new vulnerabilities, for example, using fuzzing. And in the coming weeks, I will release new details about Apache HTTP security, including new bugs. So stay tuned. So that's the end. Thanks to all of you for attending. And now it's time for the questions. Thank you so much.